So every algebra student learns how to graph a function. But unfortunately, I think it's really easy to lose sight of exactly what the graph of a function is, and even what a function itself really is. I've heard many teachers describe a function like a machine that takes some input number and transforms it into some new output number according to some rule. So maybe this function takes the input number, which is usually called x, and adds 4. So it would take a 3 and output 3 plus 4, which is 7. Or maybe it takes in a 12 and outputs 12 plus 4. Or maybe it takes in negative 4 and outputs negative 4 plus 4. And yeah, that is a perfectly valid way to think about what a function is. But I think it sort of gives the impression that a function is just like something you do to a number. This function adds 4. Maybe this function takes the input number and multiplies it by 5. But really, a function is a mathematical object, like how a number is a mathematical object. And just like numbers have properties like they can be positive or negative, they can be even or odd, they can be prime numbers, they can be square numbers, functions can have lots of different properties as well. And sometimes the best way to see what those properties are is by looking at the graph. Now, some of you may have learned how to graph this kind of function, and maybe you did it by finding the slope and the y-intercept and using that information to graph the entire function all at once. But I'm going to do it just by taking some input numbers and seeing what output numbers the function gives us. And I'm going to do it that way because even though it can be a lot of work and it doesn't always give you the clearest picture of the graph, it does give you a very clear connection between the graph of the function and the function itself. And also, because it works for any kind of function, even if you have no idea what the graph is going to look like. So let's make a function. Let's call this function f. This can be read f of x, and it just means f is the name of the function. You can name a function anything you want. It can be a single letter, a symbol, or an entire word. I'm just going to call this function f. And x just means that x is what we're calling the input number. So f of x. And f of x is going to be 3 times the input number x minus 2. Okay, so let's try some different input numbers and see what different output numbers we get. I'm just going to make a little table here to keep track of them. And I'm going to choose these 5 input numbers. You can technically use whatever input numbers you want, and depending on which inputs you use, you'll see a different part of the function. Oftentimes, if something interesting is going to happen, it's going to happen near 0. So I'm choosing numbers that are close to 0. Okay, so if we plug in negative 2, if we use negative 2 for the input, then we get 3 times negative 2, that's negative 6, minus 2, so we get negative 8. If our input is negative 1, we get 3 times negative 1, so that's negative 3, minus 2 gives us negative 5. An input of 0 gives us 3 times 0 minus 2, which is negative 2. An input of 1 gives us 3 times 1 minus 2, so that's 1. And an input of 2 gives us 3 times 2 minus 2, which is 4. And so what we're going to do is we're going to come down here to our coordinate plane, and we've got an x-axis and a y-axis. They're just number lines. The x-axis you can see is a number line. We've got 0 in the middle, positive numbers on the right, negative numbers on the left. And the y-axis is a number line that's just vertical. So it's still got 0 in the middle, positive numbers on top, and negative numbers on the bottom. And what we're going to do is we're going to plot the input on the x-axis and the output on the y-axis, which is why sometimes your teacher might call the output y instead of f of x or something like f of x. So we are going to take an input of -2, so we'll find -2 on the x-axis, and it gave us an output of -8, so that's on the y-axis down here. And where these two lines meet, we're going to put a point, and that point is going to be on the graph. -1 was our input here, and it gave us an output of -5. So where those two lines meet, we'll put a point. Next, our input was 0, so we find that on the x-axis, it's right in the middle, and then the output was -2. Here we have an input of 1, so that's on the x-axis. The output is also 1, so that's on the y-axis. And finally, we used an input of 2, so that's here on the x-axis, and we got an output of 4, so that's here on the y-axis. And so what we've done is we've taken 5 numbers and used them as inputs for the function, and each one gave us an output. So our 5 input numbers turned into 5 output numbers. And then we used each pair of an input with its output to graph a point on this plane. And so we ended up with 5 points. And there's a lot more than 5 points on the graph of this function. These are just the 5 that we found from the 5 input numbers that we chose. And it sure looks like they're in a straight line. And it is a line. It is a line, which is why this kind of function is called a linear function. And in fact, it's not just a bunch of dots in a line. It's actually a line. And what I mean by that is, if we pick some number that's not a whole number, like maybe right here, 1.5, which is the same thing as 3/2. If we were to use that as an input, and we put it into our function, and we did 3 times 3/2 minus 2, we would get an output of 5/2, or 2.5. And so we connect the dots, not like because it looks better or anything, but because these numbers in between the whole numbers are perfectly valid inputs for our function as well. And they give us outputs that fit the same pattern. In other words, the points they generate still fall on the line. We can't possibly test all of them, but you can test a few of them if you want. Don't just take my word for it. Okay, we're going to try another function that is maybe a little bit more interesting. So we're going to call this function g, and g of x is going to be x squared, or x to the second power. Okay, and so I'm going to make another table for our inputs and our outputs. And I'm going to use a few more numbers this time. I'm going to go from -3 all the way up to 3. Okay. And just for fun, let's start over here at the positive end this time. So if we use 3 for our input, okay, 3 squared, or 3 to the second power. Remember, that means 3 times 3. So we're going to get 9. Okay, if we use 2 for our input, 2 to the second power, or 2 times 2, is 4. 1 to the second power, 1 times 1 is 1. And 0 to the second power is 0. Now, -1. negative 1 to the second power, that's negative 1 times negative 1, that's going to be positive 1, isn't it? And if we use negative 2 to the second power, negative 2 times negative 2, we get positive 4. And negative 3 to the second power, likewise, is going to be positive. It's going to be positive 9. Okay, so let's see what our function looks like. See what our graph looks like, I should say. We had an input of negative 3 and an output of 9. So that's going to be right here. Then an input of negative 2 gave us an output of 4. An input of negative 1 gave us an output of 1. 0 gave us 0, so that's going to be right here at the origin. An input of 1 gave us an output of 1. An input of 2 gave us 4. And 3 gave us 9. And so this graph is not a line. And in fact, it's not that easy to draw. So, at least not by hand. So I also have this, which was drawn by a computer and looks much better. But you can see that the version that we got just by plugging in these points is exactly the same as this. This is just more precise. So this is definitely not a line. And in fact, strangely, it sort of goes upwards on both sides, okay? Unlike our linear function over here, which goes upwards on one side and downwards on the other side. And I want you to convince yourself that that's true. If you plug in larger and larger positive inputs, like 4, 5, 6, into this function, that you will actually get larger and larger positive outputs. And in fact, they go up more and more quickly the farther you go. And likewise, if we plug in larger and larger negative inputs moving to the left, we still get larger and larger positive outputs. Also, unlike the linear function, this function has a graph which is symmetrical. It has a line of symmetry. In fact, the y-axis is its line of symmetry. So these are just two different types of functions with two very different types of graphs. But there are lots of kinds of functions with lots of very different graphs. And I've got a couple more that I want to show you. So this is the graph of a function which is x to the third power, the input number to the third power. Okay, and it gives you a graph that looks like this. It's not quite a straight line, but it does have some things in common with the linear function. But it also has some things in common with this function. And I want you to maybe think about why an exponent of 2, like x to the second power, would give you a graph that goes up on both sides. But this function to the third power gives you a function that goes up when you plug in positive numbers and down when the inputs are negative. Here's another function. This one is 2 to the power of x. So this time the inputs are the exponent. Okay, so instead of the input being the base to some exponent, here the input is actually the exponent. Okay. Here's one that's a little bit more complicated, but it has a really interesting graph. It looks like the top half of a circle. And in fact, it is the top half of a circle. If you had the bottom half of this as well, it would be an exact perfect circle. And this is the one I really wanted to show you the most. Because to me, at first glance, this almost looks impossible, that a function would actually behave like this, that it goes up and then down and then up again. In other words, as the input gets greater and greater and greater, the output gets greater and greater and greater, but then it turns around and it starts decreasing, it starts getting lesser. And then it turns around again and starts getting greater, and then it does that forever. It seems insane, but this is a real function with a real equation, a real rule that makes this happen. It's quite a bit more complicated than the functions that we graphed by hand, but it is a real function. There's no reason you couldn't do it by hand. And this is the kind of thing that I was talking about when I said a function is an object. It's not just something you do to a number. It's something that's got its own properties, its own almost personality.